Let's do question 834, sum of distances in tree. This is a diabolical question, which I hope no one gets asked in an interview. There's a pretty straightforward brute force, which will time limit exceed. The optimal solution is a little bit complex, but bear with me. So we have a tree, and we want to return a list of lengths. The node at index 0, node 0, the first item in our list, that should be the sum of the length of all the paths from this node to every other node. So let's look at how you can work this out. The path from node 0 to node 1 is this, which has a length of 1. The path from 0 to 2 is this over here, which has a length of 1. And the path from 0 to 3 has a length of 2. So we know from 0 to 1, the length is 1. From 0 to 2, the length is 1. From 0 to 3, the length is 2. From 0 to 4, the length is also 2. And from 0 to 5, the length is also 2. So if we add 1, 1, 2, 2, and 2, we know that sums to 8. And 8 is the first item in our answer array. So for node 1, the path from 1 to 0 is 1. The path from 1 to 2 has a length of 2. And the path from 1 to 3 has a length of 3. Likewise, for 1 to 4, there's a length of 4. And for 1 to 5, there's a length of 5. If we add 3, 3, 3, 2, and 1, we end up with 12, which is the second item in our output array. So we can see how to form this output array. For each node that we have, which is labeled from 0 to n-1, we can calculate the path length between that node and every other node, sum that all together, and add that to our output. So that illustrates the brute force approach. Let's go ahead and implement that, because in an interview, you want to get something on paper. And then we'll talk about the optimized version afterwards. So let's go ahead and implement the brute force. So let's start by making a distance array, which is going to be our output. We said we want to check each node against every other node. So we can do a nested for loop. And check if they're the same node or not. If they're not the same, we're going to want to say the distance array of the node, which is going to contain the sum of all the distances or the length of the paths from that node to every other node in the tree. We're going to want to add to that the distance between that node and every other node in the tree. So let's say we have a function dist that takes in the start node, the other node, and let's just pass an empty set because I want to do DFS. Let's define our dist function. It will take in the start node, a goal node, and a visitor set. So if the start node is equals to the goal, we want to return steps. And I've missed that variable, steps. And let's pass in 0 for the initial value. If the start node isn't the goal node, we'll say visitor.addStart to say we've seen this node. We're going to now want to look at all adjacent nodes in the graph. If we have not seen this node before, if we haven't seen the adjacent node before, we should explore it. And if we have reached our goal state, we know we are done. So we can say maybe steps to goal. That's going to be dist, the adjacent, the goal, steps plus 1, because we're taking one step to get to the adjacent node, and visited. Maybe steps to goal. We can return that. Otherwise, we keep looking. And if we find nothing, let's just return -1 here. Cool, that looks fine. We need to create our graph. So our graph, we're going to make it a dictionary. for each edge, I'm going to want to check if edge of 0, not in graph, let's add it. So that's looking pretty good. We've made our graph. We have a function to calculate the distance between a start and a goal. And we have a for loop that checks every pair of nodes. So this is going to be our set of start nodes from 0 to n-1. And we're going to say for every other node here that isn't equal to the start node, add it to the distance array, return the distance array. So that should do what we want. Cool. So as you can see here, we've exceeded the time limit on test case 64. So let's think about how we can do a bit better. When we do this calculation, is there anything that we can maybe reuse? So going back to the very first thing we did, calculating the sum of the distances between 0 and every other node in this tree. So we have 1, 2, 3, 4, 5, 6, 7, 8. We know that the sum for index 0 is going to equal to 8. Let's say instead of making index 0 our root, we want to make index 1 our root, or node 1 I should say. So let's do that in another color. I'm feeling blue. So if we want a root around node 1, how do our distances change? Well, from node 1 to node 0, we have the length of 1. From node 1 to node 2, we have the length of 2. From node 1 to node 3, we have a length of 3. Node 1 to node 4, there's going to be a length of 3. And from node 1 to node 5, there's also a length of 3. When we sum that all up, we know from node 1, that's going to equal to 12. Something a little bit interesting is the 3's that we have here from node 1 to node 3, node 1 to node 4, and node 1 to node 5. Before, when we were looking at node 0, these were 2. So the length of the path from 0 to 3, that was 2. From 0 to 4, that was 2. And 0 to 5, that was also 2. As well as the path from 0 to 2, that was 1, which now becomes 2 when we make 1 the node of interest. So what can we see from this? If we split at the prior root, which was 0, everything that was on the right-hand side of 0 got incremented by 1. If you look at the past here, these have all been incremented by 1. Why do you think that is? When we move the root to the left, it moves it 1, which is this edge over here, it moves it 1 away from everything in the right. So can we take the parent value, or the parent sum, the parent of 1 is 0, and can we kind of formulate some sort of expression? So we have 8 here. We know we need to increment by 1 everything on the right hand side. So this is going to be an R here. And this is the left hand side here. So on the right hand side, how many nodes are there? There's 1, which is node 0, 2, node 2, 3, node 3, 4, node 4, and 5, node 5. We need to increment all that by 1, so let's add a plus 5. There are 5 nodes here. Have we this right hand set? We can denote that as nodes that are now further away. Because prior, the value of 8, we got that from making 0 our root and doing the calculation. Now we will make 1 our root and do these calculations. This entire segment got further away. But did anything get closer? Before, when we had 0 having a sum of 8, we had a length of 1 here, this edge here, to get from 0 to 1. Now, when we have 1 as our new root of interest, get to 1, the sum is 0 because we're already at 1. So effectively, we move everything on the left half over here closer. So when we move everything on the left-hand side closer, we need to subtract 1, or subtract everything on the left-hand side, or the number of things on the left-hand side, which is just the node 1 here. And we can formulate this expression now. So 8 minus 1 plus 5, that equals to 12. And 12 is also the number for index 1, which is node 1 here in our output. So that looks like that works. Let's see if that works for index 2, for example. If we make 2 our root of interest, how many things do we bring closer? Well, that's everything in this segment over here. Let's just call you segment C for closer. We now know that our parent value was 8. The number of things we have moved closer, so we can subtract, is 4. Because there are 4 nodes that prior, from node 0 to node 2, there was a path sum of 1, and from node 0 to node 3, there was a path sum of 2. Those path sums are now 0 to get to node 2, and 1 to get to node 3. So they have decremented by 1. So for the path from 2 to 3, it's 1. From 2 to 4, it's 1. From 2 to 5, it's 1. And from 2 to 2, it's 0. Whereas prior, when 0 was a node that we routed around, it was a path of 2 to get to 3, a path of 2 to get to 4, a path of 2 to get to 5, and a path of 1 to get to 2. It kind of makes sense that we want to remove 4 things over here. So what have we moved further away this time? Well, this set here, let's make you F for further. We've moved 0 further away. The sum to get to 0 now is 1. Whereas before, since we routed around 0, it was 0. And we move 1 further away. So the path to get from 2 to 1 is now 2. Whereas before, it was a path of 1 to get from 0 to 1. So we know we need to add 2 things. And that sums to 6. And 6 is the sum of distances between node 2 and every other node in the tree. So we can see this works. So how do we calculate this for one of the children of node 2? So we know the path from node 2 to node 3 is 1, 2 to 4 is 1, and 2 to 5 is 1. Let's say we're interested in node 4. So now we're routing around node 4. And we know the prior value, the sum between the distances of node 2 and every other node, that was 6. So let's look at node 4. If we root at node 4, what things do we bring closer? Well, it's actually just this segment here for itself. So let's make that C. We know prior we had a value of 6 when we routed around 2. So we'll say 6. And we brought one thing closer. Prior to get from node 2 to 4, the path was 1. Now to get from node 4 to 4, the path is 0. So we brought one thing closer. Let's minus 1. How many things do we bring further? So F for further is everything else here. So node 5 is further away. Prior, we could get there from node 2. There was a sum of 1 to get to node 5. Now it's 2. We have to go 4 to 5. So we have 5, 2, 3, 0, and 1. That is 5 things that are now further away. So we have to add 5. And when we calculate this, this sums to 10, which correlates with the answer for the fourth value in our output. So the sum of distances from node 4 to every other node should be 10. And that is correct. That correlates to the answer of the fifth thing. Remember, it's from 0 to n minus 1 in our output answer. What can we exactly formulate around this? The number of things we bring closer is the size of the subtree at the root. So for 4, it's going to be 1. For 2, we brought 4 things closer. So we brought 2 closer, we brought 3 closer, we brought 4 closer, we brought 5 closer. So that's going to be 4 here, which is the size. And for 1, we only brought 1 thing closer, which was 1 itself. So the number of things we brought closer, which is the thing that we subtract, so let's say C, this is this part of the equation here, which is the size of the subtree at our new root. So what is the number of things that we bring further away? That's going to be the number of things in our tree. So in totality, we have 6 nodes here. So 6 minus the number of things that we brought closer. So we brought 1 thing closer here. So we minus 1 here, and that equals 5 here. So the things that are further away, let's say F, that's going to be n minus the number of things that are closer. And what do we have to start our equation with? We have the sum of distances from the parent node to every other node in this tree. So we base it around 0, having a sum of distances between it and every other node as 8. Then we went down to look at the sum of distances from 1 to every other node, and we worked out that was 12. We then went over to 2 and worked out the sum of distances between 2 and every other node. And for both the calculations for 1 and 2, we based it off this 8. And then when we went to look at 4, we based the calculation off this 6 over here. So the start of the equation is nothing but the sum of distances from the parent node of the current node we're at. So I hope that makes sense. In essence, we start at rooting at the lowest value of 0. This allows us to get a sum to work with. So we had 8 before, and then we go to its children. For each child, we'll work out this equation here. Let's say parent sum, so let's say PS. I'm going to then add to it the number of things that are further away, so let's call you F. I'm going to subtract from it the number of things that are closer, and that is our equation. Now the number of things that are closer is going to be the size of the subtree we are now rooted on. So when we went to 1, that size is 1. When we went to 2, that size was 4. And when we went to 4, that size was 1 as well. The number of things that are now further away is n minus the size of the subtree we are now rooted on. Because when we went to 4, the size of the subtree rooted on is 1. The size of everything that is now further away from the calculation from 2 here is going to be every other node in this tree. When we went to 2 here, we made this part further away, and so the size of that is going to be n minus the size of this subtree, which is 4. So we have 6 minus 4, that's 2 nodes. These 2 nodes move further away. So let's use that to code up a more optimal solution to this problem. Start by removing the prior dysfunction that we had. We don't need any of that. We can keep the graph stuff. So we need to calculate the sum of distances from the root. And we can start as the root being 0. And we also need a way to calculate the number of things we move further and closer. The things we move closer is the size of the subtree at a particular root we're at. For example, at 2, we move 4 things closer. And the things we move further away is n minus the size of the subtree of 2. So move 2 things further away. And we can see that that is to do with the size of the subtree that we are rooted at. So we also need to calculate the size of the subtrees that are rooted at each node in this tree. We can do that by keeping a dictionary of values. We can have the number being correlated with the node. So for example, we can do this by keeping track of the sizes in a dictionary. So subtree size will be keyed by a value that represents the node, so 0 to 5 or 0 to n minus 1, where the value is going to be the size of that subtree. We can do this calculation in one DFS or one traversal. You could also use a BFS. And after that, we know that we need to calculate based off the parent, the number of things we move further and closer away for each node. We know the calculation is going to be parent sum minus the things that are closer, num closer, let's call you that, plus num further away, which is going to be n minus num closer. We know that n minus num closer is going to be num further. And we can do this in a second DFS. So let's go ahead and implement those. So we can make a function dist from root. We're going to say the root node is always going to be 0. I'm going to say there's going to be a current node here. There's going to be a length, the length of the path, and visited is going to be the set of nodes that we've seen. We can start by saying we're going to add to the distance array, which is our output. We're going to add the length of the path we're on to that. As we traverse this DFS, we're going to go 0 to 1. That's a path of 1, or length of 1. We go back to 0, then 0 to 2. Then because it's a DFS, we'll go 2 to 3. At that point in time, our length of this path here is 2. So we can add that to our distance array of index 0. We do the same for 4 and 5. So now our distance array of index 0 is going to have the value 7. And then we'll go back up here. We then add the length at 2, which is going to be 1, to the distance array of index 0, and that gives us a total of 8. We're also going to want to collect the subtree size. So we can start at a size of 1, which is just node itself. Now we're going to want to say we've visited the node. Now for each adjacent node in our graph that we have not visited, we want to then explore that node. We increment the length of the path by 1. Then once we've explored that node, so for example, we went from 0 to 1, then 0 to 2, we're exploring the node of 2. We're going to want to explore an adjacent node. So let's say 2. Once we explore all of 2's children, we know 2's subtree size is going to be 4. And then we can add the adjacent node subtree size, which is this 4 over here, to the current node. Node 0 is the current node subtree size, so we can add 4 to that subtree size. So we can then call this function And let's just print out the subtree sizes to make sure that we have that right. Whoops. So we need to make this node. So if we have no edges, we should return nothing as well. So let's just do this here. So let's run that and see what our subtree size is. For the first input, which is example 1, we have node 0 has a size of 6, that's correct. 1 has a size of 1, 2 has a size of 4, 3, 4, and 5 have a size of 1. Perfect. So our first DFS should be good. Let's then go ahead and calculate, based on the parent, the distances between the new node that we're going to route around and every other node, and we do that with the things that move closer and the things that have moved further. So let's just say call you calc routes. We'll start with a node. We're going to want the parent sum, and we're going to want a visited set. So we can start by adding to visited the current node. Our calculation was going to be the dist array, which is the output of node, should equal the parent sum minus the number of things that are closer, which we should be able to get from subtree size. So subtree size of node. And then we also need to add the number of things that are further away, which is n minus subtree size of node. So we can do that. And then for each other node, we want to then do a DFS to fully explore this graph or tree. A new parent sum that we pass down into this calculation is this value here that we just calculated. And we'll pass visited. And when we call this, we can do calc routes. We'll start at 0. We actually know the sum of the distances between 0 or the root and every other node because we've calculated that here in the prior call or the prior DFS. So we should be able to pass in dist array of 0, and we'll start with an empty set, and we can skip this calculation here if the node is 0. Cool. So after this, let's print our dist array and see what we have. So that, oops, that should be not equal 0. So let's try this again. And our distance array looks correct. So instead of printing it, let's return it. Almost. So if there's no edges and n equals 1, yeah, I guess that makes sense. We should return 0, and this is, okay, cool. That should be 0. So let's run this. So n has to be at least 1. So if there's no n edges, that means we just have one thing, return 0, because the path sum would be 0. So let's go ahead and submit this. Awesome, it looks like it works. Maybe on the slower end of the runtime, but if we look at the solutions up here, they roughly look similar with 2 DFSs. So it's good enough for me, it's good enough for your interviews. Again, I hope no one gets asked this in a coding interview, and I hope this was helpful.